All right. So, notes week 5, part 2, we're learning about Newton's laws. So, Newton's third law says for every force there's an equal and opposite force. And the example that I like to talk about is this. So this is not shown to scale, but we have the Earth and we have a happy physics teacher jumping. And so as you're jumping, you definitely feel the Earth pulling downward on you. And what's hard to believe is that you are actually pulling up on Earth with the same force. So that's the way things work. Earth is very massive. We'll draw a really big M. And I, relative to the Earth, am very not massive. So the acceleration that I experience is very great relative to the acceleration that Earth experiences. So we can say this. We know F equals ma, and the force that each of us, meaning me and the Earth, experiences is the same, or the magnitude is at least. I get pulled downward by Earth, and I pull Earth upwards. So the same force means that for me, mass times acceleration is the same as mass times acceleration for Earth. ma equals ma, and maybe I should use a big M for Earth. Yeah, here, I'll draw it like this. Sorry, erase that or cross it out or whatever. So me, let's see, I have a little tiny mass and so a big acceleration, and Earth has big mass and so small acceleration. All right, so instead of actually writing in big numbers, this is kind of how we can represent that. But for every force, forces do not exist in isolation. They come in pairs, and so we call those action-reaction pairs. And if we look at, let's call this a box on a desk, we have an action-reaction pair going on here. And one is that the box is pushing down on the table. So this is box pushing, I'll say everything, I'll write everything, just to be thorough. Box push down on table. And the opposite of that is the table pushes up on box. And so that's the way things work. When you push on the door pushes back on you, and you can actually feel that. Okay, and they're going to have equal magnitude, opposite direction. That's some good vocab right there. Equal magnitude, magnitude meaning amount. Equal magnitude, opposite direction. Okay, hey, direction. So, action-reaction pairs, that's different from a free body diagram. And so we've talked about free body diagrams, or maybe we haven't, but the idea behind a free body diagram is we're pretending whatever object we're interested in is free of other stuff around it, okay? So, free body diagram for the box, we're just considering forces acting on object. And if we think about the box, there are two forces acting on the box. One is gravity pulls downward, and so we can call this the force due to gravity, aka weight. And the force that opposes that, so the box is just sitting there on the table, it's not accelerating, the net force on it is zero, it is in equilibrium. It's a lot of terms right there. But basically, the two forces acting on it cancel out. And so gravity, or its weight, pull downward, and table push up. Table pushes up. Caveman speak. Okay, so a free body diagram would actually be like this. We wouldn't draw the table. We would just draw the box. And sometimes people are particular about the forces emanating from the center of the object. That's not a big deal, but it's basically like this. So we could say gravity and we could say table. Notice how I've drawn those arrows so that they have the same length within artistic license, indicating that they have the same amount of force, the same magnitude, or the same number of newtons, but are in opposite directions. Okay, so that's a free body diagram. The excellent question is, if everyone in the world were to come to Mammoth, I know it'd be pretty crowded, feel like one of those, imagine the lines at Vaughn's, ha ha ha, and jump up to a height of 1 meter, for the sake of example, what acceleration would the Earth experience? You know, would we cause an earthquake? And if we did, would it be a magnitude of 1 on the Richter scale, or a magnitude of 9, and would buildings crumple and all that kind of stuff? So there are some things we'd have to assume, but we could definitely calculate that. And I think that's going to be an extra credit project for you. So difference between net force and normal force, because both of these involve ends, and I hear students kind of not really use these terms correctly. So let's first draw a free body diagram of an airplane, and this will help. So the airplane looks like this, obviously. It's my Shamu airplane. And when the airplane's flying through the air at a constant speed, meaning the force in the forwards direction and the force in the backwards direction cancel one another out. It has no net force in the forward direction, and it is not accelerating, okay? And constant altitude, meaning the force in the upwards direction and force in the downwards direction are also balanced. So our cute airplane looks like this, where we have a force in the forward direction, and that's due to the engines. I didn't draw my airplane with the engines, but you know. And so in terms of aeronautics, we call that thrust. So that's the force in the forward direction. And the plane in the real world is obviously going to experience air resistance. Planes take a huge amount of fuel, for example, to fly to New York, as compared to putting those people on a bus. And then gravity obviously pulls downward. And if you call this gravity or if you call it weight, those are both perfectly acceptable. And then the airplane has these funny things sticking off of it called wings, which help provide what we call lift. So those are these are some aeronautics terms that aren't on the list of things that you have to know, but here's a free body diagram of an airplane, and so we can say some things. We can say that the net force on it is 0. Okay, 0 newtons. That does not mean that it is not moving. The plane is obviously moving. What that means is that there is no acceleration. Okay, no acceleration, meaning the constant speed. Okay, we can also say that the plane is in equilibrium. And equilibrium means, sorry to be writing all over my writing, equilibrium means the forces are balanced. Forces are balanced. Okay, so there's our free body diagram. We didn't draw any planes or pelicans or whatever. But let's talk about net force versus normal force. And so by net force, I know some people think of like Spider-Man or whatever with these nets. Net force, so that is the result of all the forces. That's as a result of all. Sometimes people describe it as the sum of all the forces, and so that's fine as well. But the idea is that when we talk about the net force, and so this is how you'll see it written, F sub net, the net force is what we are referring to in F equals ma. So that right there is the net force, meaning the result of all the forces acting on the object that thus cause it to accelerate. So in the case of the plane, the net force is 0, and its acceleration is 0. In terms of a box sitting on the table, we definitely have experience with this. Table pushing up, gravity pulling down, and the net force is 0. The forces are balanced. That says 0 newtons, not on. Okay, result of all the forces. Now, normal force, F sub capital N, normal is a mathematical term that, and we brought this up before, but I'm going to say it again because at this point, if you don't know it, it's important. This means perpendicular. All right, so normal to a surface, all these little lines I'm drawing, these are normal to the surface. If I get a buzz cut, my little hairs stick up, normal to the surface. And so it's indicated like this, and in the case of the box, the normal force would be the force on box perpendicular to table. And in the case of, well, so in the case of the box on the table, it's the force of the table acting on the box. It's not a free body diagram. We're not calculating the acceleration due to gravity. We're just talking about the normal force. So that term comes up a lot, and I thought it important to mention. Let's take a look at page 2 in the second video, because we're going to run out of time. All right. Let's take a look at the second part of Notes Week 5, Part 2, where we work through a couple examples. So our first situation is like this. We have the ceiling, a frictionless pulley attached to both the 8 kilogram mass and to the 1 kilogram mass. So obviously the force downward here is greater than the force downward here. So in a tug of war, the 8 kilogram mass wins. But this pulling upward on the 8 kilogram mass is going to reduce its effective weight. So we have this situation, and in essence what we're trying to do is figure out what would the reading on the scale be. And so you can imagine yourself standing on a scale and holding onto a pull-up bar, and as you pull up more, it's going to reduce the reading on the scale until eventually you're actually doing a pull-up, and you're off the ground, and the reading on the scale would be 0. So when we take a look at what's the net force on the 8 kilogram mass, this is not entirely correct. But I want to talk about the free body diagram first. So if we talk about a free body diagram, we're looking at all the forces acting on the object. So here's the object itself. Gravity, Earth, pulls downward with a force of this. This we say is the weight of the 8 kilogram mass. The 1 kilogram mass pulls upward with a force of 9.8 newtons. And then the scale is also pushing upward. And technically we should draw the arrow from the middle, but it would get messy. The scale is also pushing upward. So the net force, the 8 kilogram mass is not moving. Okay, it's not accelerating. So the net force on the 8 kilogram mass is nothing. It's 0 newtons. So I'm going to make my zeros like that so it doesn't look like I'm writing on. Okay, so that said, when we talk about the net force, technically it's 0 newtons. But when we want, so I'm going to write that. All right. Slow down, Torville. Okay, so net force is 0 newtons. 0 newtons. What I was doing here is figuring out, so from W equals mg, and W equals mg, we get the downward force due to gravity, and we get the upward force due to the 1 kilogram mass. And when we subtract them, you see how they're in opposite directions. When we subtract, we end up with this. So this is gravity minus the upward pull, so I'll say upward pull of 1 kilogram mass. And this, so this is the result of those two forces, or the net force of just those two. Okay, forget about the scale. And that's going to end up being the reading on the scale, which is the normal force. So let's turn back to 16.6. Let's turn back to this. All right. So the difference, we know that the net force acting on, it's not moving, so the net force on this is 0. And if there's 78.4 newtons downward and 9.8 newtons upward, we know that the difference between the two is going to have to be this, which is the reading on the scale, which is also F sub n normal force. So what was that? 68.6 newtons. So to think about this question, you're thinking, is the mass moving? No. So the net force on it is 0, and therefore draw a free body diagram, all the forces acting on the object, and know that the result of all these has to be 0. And then calculate what you can from W equals mg and W equals mg, and then from those you can figure out this. So that's the normal force. It's the reading on the scale, and the net force on the 8 kilogram mass ends up being 0 newtons. Okay. So here's, I say always true. It's nice to know when something is always true. Reading on the scale is the normal force exerted by the scale on the object. We're going to do definitely some questions with scales. So that's good to know right there. Okay, next example. We have Joey standing on a scale in an elevator. And this is pretty fun if you haven't done this before. You definitely should to look at the reading on the scale. There's some videos on YouTube and stuff that we can take a look at. So I wrote down given information. Joey has a mass of 70 kilograms. The acceleration, so he and the elevator are accelerating upward with an acceleration of 2 meters per second squared, and we know that the acceleration due to gravity is negative 9.8 meters per second squared. Okay. So, question says, Joey standing on a scale in an elevator accelerating upward at 2 meters per second squared. First, what is Joey's weight? So forget about the fact that he's in an elevator or that he's accelerating. W equals mg, this is Joey's weight. Meaning on Earth, not accelerating, this is what a scale would say if you had a scale that would measure in newtons and if he were to stand on it. However, Joey's he's standing in an elevator that is accelerating. So what is the reading on the scale? So we're using Newton's second law, for F equals ma, and we're recognizing that F in F equals ma is the net force. And so if we were to draw a free body diagram, here's our free body diagram for Joey. So here's Joey. We have an arrow upwards, and that is the scale pushing on Joey. He's standing on the scale. And so that is a force in the upwards direction. And then gravity pulls downward. And I meant to draw this arrow a little larger because he's accelerating upward. I just know before I even start solving stuff that the force upward is greater than the force downward because Joey's actually moving. This should not go in a free body diagram, but Joey's actually moving in that direction. So we understand that this force is going to be greater than this force. Okay. So our free body diagram, here's Joey. Scale pushes upward on him, Earth pulls downward on him, and we know this is called the weight, and we have already calculated that it is 686 newtons. So we're interested in what's the reading on the scale. And I'm going to say, how many newtons? So question newtons. Now, based on this upward and this downward, we can say that the net force, you see how we have the scale pushing upward. So when we talk about net force, the result of the two forces, these are in opposite directions, and so it's going to be scale minus weight, because those are in opposite directions. And that's the net force. So when we substitute in, right over here, 2 net force equals mass times acceleration. Here's our net force, scale minus weight equals mass times acceleration. And solving this, oh, I didn't even solve this. Sorry. Good thing calculator's over here. Alright, and so solving, we have 70 times 2 would be 140. So let's go, I tend to abbreviate reading on the scale like that. minus 680 equals 140, and we'd add them together. I don't need a calculator for this. Reading on the scale, 140, 680, 780, and 820 newtons. Okay, so notice how he's accelerating upward. The reading on the scale is more than his actual weight. This is called an apparent weight, meaning based on some situation like acceleration, the scale is reading something different than from his actual weight. Okay, last part of the question. If the cable supporting the elevator were to snap, what would be the reading on the scale? So here is Joey, here's the scale, and here is the elevator. These three objects all have very different masses, okay, light, medium, heavy, but like Galileo said, like the hammer and feather, they're all going to accelerate at the same rate. And that rate at which they're going to accelerate is negative 9.8 meters per second squared. And so they would kind of be Joey and the what's this thing called? A scale would be floating inside the elevator. This does not say on, this says 0 newtons. So 0 newtons would be the reading on the scale. And let's hope that doesn't happen to Joey. We like him.